we'll walk through and we'll try to fill in some of those missing blanks. Like I said, I know the video goes fast. All right, so let me find our handout. All right, here we go. All right, according to the presenter, the basis of statistical inference. Now, this is not new to this unit, okay? The whole idea of statistical inference is that if we are trying to figure out something about a population, we take a sample and we try to take that information and infer it back to the population. So the basis is we are trying to estimate a population parameter from a sample statistic. So the common ones that we've been doing is sometimes we might calculate a percentage or a proportion. We might calculate a p-hat, and we try to use that to estimate the population proportion. Or the other one that we often do, and this is what they were doing in the video, they calculated an X bar and they were trying to use that to estimate the population mu, okay? Now, the way your book is set up is 8.1 is just an overview of confidence intervals, and then 8.2 is going to go through all the specifics if you're doing percentages and proportions. And then 8.3 is going to go through all the specifics of X bar. Please keep in mind the video focused just on the X bar, so it really was more related to 8.3, okay? All right, rather than a single number, a confidence interval will include a range of values along with a confidence level. Now, the most common confidence levels are 95, as they use in the video, or 90 or 99. Someone asked me last hour, she says, well, how do you pick? And I said, it's a very delicate balance for a statistician because there's a lot of things to consider. Okay, and I'll talk more about that when we get into the actual 8.1 notes. All right, two things you have to consider. You want a normal distribution because you saw in the formula, it uses Z in the formula. Now, if you don't know that it's a normal distribution, now we're going to go back and you would have to know how to go through the normal condition. If you're doing P's, then you get to your NP and N times 1 minus P. If you're doing X bars, you'll have to apply the CLT. So that stuff is not going away. And then, of course, you want a good random sample. And that would refer us back to what we learned in chapter 4. If you don't take a good random sample, everything you do is garbage, okay? All right, so why is the rack used? Now, to be honest, this is not necessarily even an important concept for chapter 8, but I thought this is important to notice, again, going back to chapter 4. They mentioned they needed a controlled environment, okay? A controlled environment. And he talked about the fact that it might be more fun to test batteries in the fun little toys like the parrot with the flapping wings or the little helicopter drone. But what if the helicopter drone just by design used more battery life? Okay, then all of a sudden we can't test things in the toys because the toy itself now is going to be a confounding variable. And that's why they built this thing called a rack, and all the batteries go into the rack and it just simulates battery life. Okay, so in order to create a confidence interval, all right, now they said 4 parameters. I'm actually going to change that to statistics because, of course, parameters are what we know about the population, and that's what we wouldn't know. What we have to get is a sample mean or a sample proportion. Okay, again, all of these we're dealing with X bars, but you need to know the standard deviation of your sample. Okay. Most of you did my little exercise last week, right? I made you calculate the mean for the words in the sentence or the letters in the word, and I made you write down the standard deviation. You need to know your sample size. And for a confidence interval, you actually also need to know what confidence level you're going to use. And I'm going to say it again. Which one do you use? Well, for your problems, you're going to use whichever one they tell you to do. A statistician would have to make that decision, okay? And there's a lot of things to think about. 3 assumptions. Number 1, independent observations. And she gave the example of each battery life is independent of another battery life. And I've talked about that in this class, that yes, independence, we could say if there are human beings in our sample, each individual is independent of another. I am also going to remind you at this point about your 10% condition. If it is possible to quantify this, you should. This is where you're going to say 10 times my n size. Is that less than or equal to my entire population size? You can say both if you want. Now, I've used examples before about what if you're sampling water or sand? Okay, you can't really quantify that necessarily. Okay, so then you might just say every observation is independent of the other. But whenever possible, we quantify. We want the data to be from a normal population. But we know it might not be a normal population, but could it be from a normal sampling distribution? Here we go again. If we don't know about the population, then you will have to establish the normal condition. Are you going to do the NP and N times 1 minus P, or are you going to do the CLT? You are going to be using those things for the next chapter 8, 9, next 3 chapters. Okay, they're not going away. All right. And finally, that we would need to know the population standard deviation sigma. And Party Sabetti said that actually is not a reasonable assumption. And what I remind people is, why are we doing this? Because we're trying to estimate the population mean. Well, if we don't know the mean, why would we know the standard deviation? So there are ways around it, as she mentioned in the video, but we'll worry about that another day. Okay, for right now, we're just going to say, we'll pretend we did. All right. A single number that is used to estimate a population parameter is often referred to as a point estimate. Again, this ends up being your sample statistic, your p hat or your x bar. Those are the ones that we commonly use. And again, this is going to be us in section 8.2. This will be us in section 8.3. This whole video was doing an x bar. In addition, a confidence interval will include a margin of error. I will refer to that as the MOE quite often. Okay, so when you see that little abbreviation, that's a Miss Ferrariism. So using the formula, sigma sub x bar, blah, blah, blah. All right, she said it was about 10. But as a reminder, where that came from, in the video, sigma was 63.5, and they divided by the square root of the n size, which was 40. And that's where that 10 came from. And then she started reminding you about the 68, 95, 99.7 rule. And if you remember, what we did with that is we started with mu in the center. We did 1 standard deviation out, 68%. We did 2 standard deviations out, 95%. And that's why they use the number 2. Do you remember if you were here for the exercise we did last week? Did I have you multiply by 2? I think I did in that formula. That was why. You were calculating confidence intervals on that exercise. You were doing 95% confidence intervals. Okay, that's what you were doing on that readability exercise. So this states that 95% of the readings will occur within 2 standard deviations. And to be honest, the 2 is an estimate even. We very often, instead of 2, we make it more specific as 1.96. Now, you might wonder, where did that come from? Where do we get that 1.96 from? We'll go over that another day. Okay, Party Sabetti said in the video, you can do any confidence interval or level that you want, but you will have to use a Z distribution to figure out that number. All right, for the example of the battery life, the confidence interval came out to be 450 minutes plus or minus 20. Now that 20 was the margin of error, and the 450 was the X bar. But what that also means, how we usually write the confidence intervals, we actually do the math, is we say, okay, so it could be as little as 430 minutes if I subtract, or it could be as high as 470 minutes if I add. And we write it usually using interval notation. and I hope you can see mathematically that your point estimate, whether it's an X bar or a P hat, is dead center in between your minimum and your maximum, okay? A 95% confidence interval indicates that 95% of the time, our samples will include the population parameter. And I remind you again, in the video, that was mu, but it also could be a percentage or a proportion. The general formula for a confidence interval. Now, keep in mind, this was the formula when they were doing an X bar. So you start with your X bar, which is your point estimate, and then it's plus or minus, they call it Z star. That's the number that I'm going to teach you to get from the Z distribution, the normal curve. And then you multiply by your standard deviation of your sampling distribution. That formula will change a little bit if you're doing percentages and proportions. And you don't have to flip forward, but I will. You can actually see it. It's right there. Okay, that's the formula. That's how it switches for 8-2. Okay, this is the specific formula for 8-1, or 3 rather. All right, so all of these quotes, these are direct quotes from our dear friend Party Sabeti right here. As you start going through chapter 8, you will be asked to interpret the confidence level. You might be asked to interpret your confidence interval. They're a little bit different, okay? These were all different ways that she described how to interpret the confidence level. And only one time did I hear her say specifically what your confidence interval stood for. We will talk more about that through the notes, okay? So anything that you missed along the video? Or did we get all of it filled in now? You got it? You good? All right, then I'm going to switch back to the notes packet now. I can find my place here. All right, so some of the stuff in the notes, I'm going to go through it really quickly because it's actually going to be very repetitive with what we just did. I will point out on the front of the notes packet. All right, again, 8.1 is an overall summary of confidence intervals. 8.2 will deal with proportions. 8.3 will deal with means. So we're talking X bars and mu's, and here's P hats and P's. And we are going to be learning some things on our calculators. Do not show up without your calculators. Okay, we need them. Make sure they're charged up. We're going to need them. All right, so going to go through this stuff really fast because so much of this is duplicated from what we just did, but stop me if I go too fast for you. All right, point estimate. A single number, a single statistic used to estimate a population parameter. As a reminder, we're going to be doing P hats, which are used to estimate P, and X bars that are used to estimate mu's. The margin of error is how close an estimate would be with repeated sampling. Now, in the real world of statistics, you don't necessarily do repeated sampling. You'd maybe do one sample of a whole bunch of batteries. Okay, but the way a confidence interval is set up is we are saying that with repeated sampling, for example, the 95%, we would expect that 95% of the time, our confidence intervals will contain the true population parameter, okay? All right, so the confidence interval is your point estimate plus or minus your margin of error. These are the 3 most common confidence levels. Those are the most common. You could do any, but those are the ones that people use most often. requirements, good random sample. That literally goes back to chapter 4, that we found that if we don't have that random selection, you're not allowed to infer back to the population, okay? The population should be approximately normal. And if it's not, you might have to check your normal condition for percentages, or your CLT, your normal condition for X bars. Individual observations must be independent, so we check our 10% condition. The population standard deviation will, for now, we're going to assume that we know it, okay? All right. So again, back to the question that the student had last hour. How do you decide what level of confidence you want, okay? It really kind of comes back to the formula, okay? Now, let me first talk about just the common levels, 90, 95, 99. Wouldn't it make sense that you would want to be as confident as possible? Like, I want to be 99% confident. Okay, but here's what happens. If you want to be 99% confident, picture the bell-shaped curve. If you want to be 99% confident, can you picture how far your z-scores would have to be? Okay, so you just made that value really big. And therefore, when you multiply by your standard deviation, you just made your margin of error get very big. So now you're taking the mean and you're adding a big number and you're subtracting a big number. Do you understand that you just made your confidence interval really wide? So how impressed is somebody? Like, that goes back to the cartoon that's on the front. Okay, the cartoon that's on the front of the notes page. It says, the high temperature will be between 40 below and 200 above. Okay, how confident is he? Okay, very confident. How helpful is that to you? Not very. Okay, so the issue is, your first reaction is, I want to be as confident as possible. Well, that means you're going to make such a wide confidence interval that no one's impressed now. You haven't helped anyone. Okay, I still don't really know where the true mu is. You gave me too big of an interval. Okay, back to the formula. What about the n size? N's at the bottom. So we've talked about how larger n sizes generally produce better data, right? Okay, but if your n size is large, when you divide by a large number, what happens? Okay, so you divide by a large n size and you just made this get smaller. And now when you multiply, you made the margin of error get smaller. Okay, so now you took your confidence interval and you made it smaller. Okay, so now it's really, now do you understand that now the confidence might be down a little bit because you made the window so tiny? Okay, they're all intertwined. Okay, and that's how, when people say, what level should we pick? It's like, well, I'd love to be as confident as possible, but yeah, if I do that, now my interval's so wide that no one's impressed. But, so it's a balance of all of those things, okay? The other thing I said here, think about a goalpost. My example is always Mrs. Ferrari out on the field, okay? I am not an athletic person, okay? So if you put me on a soccer field and said, Miss Ferrari, kick the soccer ball into the goal. You know how wide I want you to make that goal for me? I want it to go end to end, okay? Are you confident I'm going to make it? Okay, I'm still not. I thought, all right, but you just gave me a really wide goal. But sure, now I have a better chance of making it, but it's not very impressive, okay? So as soon as you get a higher confidence, you're so wide that it's not helpful, okay? But the bottom line is all of those things in that formula will all interact, and you make one bigger and another smaller, and it changes the math, okay? And we'll talk more about that as we go through examples. All right, so let's go through an example, and let's create our own confidence interval. So this data right here, a busy 2-lane highway has a speed limit of 45 miles per hour, but it's located near a subdivision. And the people in the sub said, people are going way too fast. Okay, you ever go through your subdivision, you see those, they have those speedometer things? Okay, they're collecting data, okay? And they're collecting data to find out where they have problems, Now, on a main road, they literally might be taking data to decide if they maybe should change the speed limit. But in a subdivision, they might be deciding where they're going to post somebody to give traffic tickets. Okay. So they set up one of those signs and they measure the speed of a random sample of 12 cars. All right. So N is 12 here. All right. So they go through and they do their calculations. A point estimate for the population mean. So they would calculate their X bar, and I'll help you out here. This X bar came out to be 59.617. And of course, what they're doing is they are using that. They're going to say, I think that means that mu is 59.617. That's the whole purpose. But can you easily understand that on any other day or any time of day, there could be a different 12 cars came through and the speeds could be different? So every time someone takes a sample, the X bar could come in different. That's why we do confidence intervals. We say, all right, we get it. It might not be 59.6. So what we do now is we say, we're going to create a confidence interval. And we're going to say 59.617 plus or minus, and now we create the margin of error. But for the margin of error, we need the standard deviation. Okay, and here's the artificial piece. Okay, if we don't know mu, why do you think we would know sigma? Okay, we probably wouldn't, but let's say we did. Then sigma sub x bar would be that 8 sigma divided by the square root of the n size, so the square root of 12 here. And I had that comes out to be about 2.309. So the rest of the formula here is we need a z star, and then that's going to get multiplied by the 2.309. And these two things together, by the way, that creates your margin of error. Now, what z star do we use? Well, since we're doing 95% again, which is a very common one, we're going to use that 1.96. So the margin of error itself is 1.96 times 2.309. So the margin of error itself is 4.526. Now, technically, that is a confidence interval right there. That really is. But it's much more common to actually do the subtraction and the addition. So I'm going to start by saying 59.617 minus 4.526, so 55,091, up to, and then I take the same math, except I change the minus sign into a plus sign, 64,143, and that is now my 95% confidence interval. I am 95% confident that the true mean speed of cars on that stretch of road is somewhere in the interval from about 55 to about 64. Okay. And that's actually what I have here. Your AP phrasing for interpreting your interval. And this is required every time you create a confidence interval. On your homework, on a test, on the AP exam, and especially on the AP exam, because typically I'll remind you, but they might not. And on the AP exam, every time you create one of these, you move right into the explanation, and you can memorize this. We can be 95% confident that the interval from, and I'll just say from 55 to 64, only because I made the blank so small, otherwise I would actually use the numbers. I am 95% confident that the interval from 55 to 64 miles per hour captures the true value of the mean car speed on this road. When you interpret your confidence interval, you are very specific about what the numbers you came up with mean. Now I'm going to back up a step. every once in a while, they will ask you to interpret a confidence level. Now they're just trying to get you to think about the 95%. Not specifically your 55 to 64, but what does 95% mean? Okay, that goes back to Party-Sabetti. All of these things, okay? To say that you are 95% confident means that we got the numbers using a method that will give correct results 95% of the time. It's very generic. It's just telling you what the 95% means, okay? 95% of the time, if I keep collecting samples and I keep making confidence intervals, 95% of the intervals that I create should capture the true mean. You can memorize this. Again, I'll just use this example. 95% of all possible samples of size n from this population will result in an interval that captures the unknown population parameter. Now, that's one thing Party didn't talk about, the n size. But understand, based on the n size has a huge impact on this formula. Okay, so if this is your method is also thinking about, I'm using a constant n size. I don't take a new sample. I don't sample once with 12 cards and then sample the next time with 30 cards. Okay, that's comparing apples to oranges. Okay, again, these are two things that you can memorize: confidence level, confidence interval. So the next example, this is actually what you guys were doing with that readability exercise. This is just a different example of it. So a very common IQ test is called the Stanford Binet. And so I used Minitab, and I had a set of data and artificial. I knew what the mu was for the data because I know what standard IQ tests come in as. They're a mean of 100 and a standard deviation of 16, okay? But I used Minitab 20 times. I took samples of size 15 from a data set that had a mu of 100 and a sigma of 16, okay? I randomly chose 15 numbers from this data set. I calculated the mean. I calculated the margin of error by doing 1.96 times 16 divided by the square root of 15. And then I subtracted, and then I added. And I came up, every one of these is a confidence interval. I did that 20 times. Okay, so again, in my computer, I have a set of data. I have a very large set of data that has a mean of 100 and a sigma of 16. And I set Minitab up that out of that data, it just kept selecting 15 numbers, okay? And out of those 15 values, I had to do this math. So these are all confidence intervals. You know, and this is the artificial part, but I'm telling you, the true mu is 100. How many of these intervals did not capture 100? How many of these intervals did not capture 100, assuming this is minimum and this is maximum? Okay, I think this is the only one, isn't it? Okay, so only one of them did not. So in other words, 19 out of 20 did. And what percent is that? 95. I was not shocked by that because I did the math using 1.96, which is the number that goes with a 95% confidence interval, okay? Now, it won't always come out to be that exact, okay? But that example actually worked out beautifully, okay? So again, we're back to the confidence level. 95% of all samples, in this case of size 15, resulted in an interval that captured the true mu.
How do we know when to say, like, this matched with a 95% confidence level versus this matched with a 95% confidence interval?
You only talk about a confidence interval because, again, as a statistician, you're not necessarily going to do 20 different samples. You're going to do like what they did in the video. You're going to take one set of blood pressure readings from a person, and you're going to do just one interval. And you're just going to say, I'm 95% confident that that interval contains their true blood pressure. Okay. A confidence interval says, if I did repeated samples, I expect 95% of them will contain the true mu. Okay. So that's why I said, will it always be exactly that percentage? No. Okay. There are so few things in statistics that are exact. All right. So the next example, I took this is from your textbook, and I used this because it was similar to the graphic that Party Sabeti kind of started doing in her video. Okay. If you do know the true mu, okay, if you really are able to calculate a true mu, and she even said in there, she goes, you usually don't ever know the true mu. But if you did and you started setting up your intervals, you can see on this one, only one was a miss. One came out way at the high end. Okay, so in this case, there were 25 different samples, and 24 out of the 25 were good. Well, 24 out of 25 actually makes, what, 96%? So what confidence level do you think they used? They probably used 95. Could they have used 96? They might have, okay? But the fact that it came in that 96% of them lined up, okay? I actually set up, I drew confidence intervals for all of your data that you did the other day with that exercise. And I'll try to remember to show it to you tomorrow, but it's actually really cool that you can actually see all your confidence intervals and see how they kind of zigzag all over. And then I do tell you what the real mu is, and you can actually see, it's like, oh yeah, there it is. You know, you just see all the intervals zigzaggy, but you see the true mu has been captured over and over again, okay? All right, so this last example, how much does the fat content of one brand of hot dogs vary? To find out, researchers measure the fat content in grams of a random sample of 10 hot dogs. There's your N size. They set up a confidence interval. So their confidence interval, and what are we doing? Measure the fat content. So this is probably an X bar, like they're doing the mean fat content. So 284 up to 755. All right, so the first thing I asked you here is, could you go in reverse? Could you take that interval and could you go in reverse and tell me what is X bar plus or minus and what is your margin of error? Would you be able to go in reverse? What would your X bar be? Oh no, they're doing population standard deviation here. So we're doing sigma. Let's call that SX for now. Would you be able to tell me what their point estimate was? 4.71? Do we have a confirmation on 4.71?
About 5,109. You just average one.
Oh, yeah.
You're going to use a midpoint formula from geometry. Add them and divide by 2. All right, so what do we get? 2.84 added to 755 equals, divide by 2, 5,195. All right, so that number should be dead center. Now, how do you figure out the margin of error? You should be able to take that 5.195 and subtract the 2.84, 2.355. You want to check your math? Take the 2.355 and add the 5.195, and it takes me to my maximum, okay? All right, so you should be able to do that. You should be able to look at a confidence interval in either notation and go in between the two. All right, here we go. Interpret confidence level. This was created with a 95% confidence interval. So for a confidence level, all you have to do is say after collecting many samples of size 10, because it's still all related to the n size, and calculating or constructing confidence intervals each time, we would expect the population standard deviation to be captured by 95% of the confidence intervals. It's very generic other than the n size. We're just saying if I took 10 hot dogs and I made a confidence interval, and then I take a different 10 hot dogs and I make a confidence interval. If I did it over and over and over again, I would expect 95% of them are going to contain mu, or in this case, standard deviation. Now, when you interpret the confidence interval, now we're very specific about the interval we created. We can be 95% confident that the interval 2.84 to 7.55 contains or captures the population standard deviation. Once you create your confidence interval, we say we're 95% confident that that interval contains the true standard deviation, or the true mu, or the true proportion, whatever it is you're calculating. Okay?
Does it have to be an unbiased estimator for you to accurately?
Yes, and that's why that's why I said that's one of the reasons I started in chapter 7 by establishing that p hat and x bar are both unbiased.
What about standard deviation?
Standard, we didn't talk about that, but I threw this in as an extra example. Okay. Now, here's the part that gets confusing for some people. When you create the interval, I'm 95% confident that I nailed it. I'm confident. But suppose I was then able to establish what the true standard deviation was. I'm 95% confident when I create it, but once it's created, now it's either what we call a hit or a miss. Yes, I know. You're not going that far. So I thought we could finish this. We just added more time to the video. Okay. The point is, once you create the interval, now it's either a hit or a miss. Either it does or it doesn't. Once the interval is created, you either nailed it or you didn't. So true or false, this interval has a 95% chance of containing the actual population. No, that is false. I was 95% confident that it did, but when it's all said and done, it either did or it didn't. Okay? All right.